The story of fully developed channel flow doesn't end actually there. There is also problem with normal stresses. If you write the normal stresses, I mean those diagonal components of the anisotropic tensor, you know that it is u1 prime squared bar, u2 prime squared bar, u3 prime squared bar. So if you write these, and then you will see that the first one will be equal to 0 because nothing is changing because the full you have a fully developed flow. The second one, because there is no velocity along 2 and 3 directions, these two will be 0 as well. So by doing the mathematics and simplifying, you can get actually this relation in here. And therefore, after you do and simplify, you will find that all the diagonal components of the stresses, the Reynolds stresses, will be equal. This is another strange result predicted by the Boussinesq eddy viscosity model. It first predicts that the shear stress will be 0, and second, it says that all the normal stress components to be equal to each other. We are seeing this. This is experimentally done by Kim et al. And back in 1987, they did DNS of turbulent channel flow. And from their paper, they found normal stress components at the center line of the channel. And these are the values of those normal stress components. And certainly these are not equal to 0. So even if you complain about experiments and say, okay, there is always uncertainty in experiments, this is the result of pure DNS. You have DNS, not experimental data. This is accurate. And normal turbulent stresses are not equal on the center line as you see in here. What we conceived from this discussion is that we try to simplify our lives, meaning that we try to actually we tried not to start effort in terms of doing LES and DLS. We tried to simplify our lives, hoping that we will directly solve for average flow field, which forces us to use turbulence models like eddy viscosity model. But at the end, we lose accuracy. This is related to the accuracy triangle that I have talked about at the beginning of this discussion. It initially may sound like a very good idea to relate the stress to a strain through some viscosity. But if you're not careful about how to reflect the correct physics that is happening in the flow, how to reflect this to the equations, this is what you get. You get all these stresses equal, but DNS says that they are not equal. Even in a simple turbulent channel flow, you get these wrong results. Imagine what could happen if you start dealing with more and more complex flows. So the second, let's say, deficiency that has been found uh, is related to the experiments of Uberoy and Tucker, and it's about subjecting turbulence to straining. They had a very simple wind tunnel, and the flow is very nice and straight. In the beginning of the tunnel, there is a turbulence grid. You see it, the turbulence grid in the beginning to generate some turbulence, and at the downstream there is a contraction. So this is an axisymmetric contraction. So you force the turbulence to axial straining. Then you do some measurements before and after straining, and then you go back to the eddy viscosity model and see if the stress values are correctly predicted by that model or not. So in the picture, we see the turbulence grid at the left. Once it passes the grid in the straight section, there is no strain. So Sij bar is 0. However, there is a very strong S11 bar component in the contraction section, as there is no mean strain in the second straight section. In here, this second straight, again, there is no strain. And if you compare it to the eddy viscosity prediction, since there is no mean strain in the right hand side section, the eddy viscosity suggests that the Reynolds stresses are 0. So this is an axisymmetric contraction. So in axisymmetric contractions, your S11 bar is S lambda, if you call it, and S2233 will be, because of symmetry, they will be equal to minus 1 or half of S lambda, let's say. Uh, so there is only one parameter, S lambda, in here that defines all this training process. Normally, eddy viscosity model uses the strain value to calculate the turbulent stress. As the intrinsic assumption suggests, you remember that we had a specific and intrinsic assumption, your Sij will be 0 in the second straight section. So the turbulence stress is equal to 0. But the experiments show that the turbulent stresses are not 0 in the second section, second straight section. I mean, I'm talking about here. You can conclude that a background history or prior history of straining is very important. So this study tells us that although eddy viscosity models can locally predict the stress, but the history of the flow is also important, which they are not able to predict. So if you are developing a turbulence model, this prior history should be reflected in the equations. You cannot just ignore the prior history or flow experience and then try to find everything just locally. So this is the second example. The third one is the comparison with kinetic energy of gases. Normally the physical viscosity of the fluid, you know that it is nu, the physical viscosity is something physical, we know it. Kinematic viscosity of the fluid, it is related to the molecular motion. So you have the physical viscosity approximately equal to half of mean molecular speed, which is c bar. Uh, this is this unit is in meter per second, and your lambda. Lambda is your molecular mean free path, which is in meters. So your kinematic viscosity is approximately equals to this. This is true for any fluid, especially for gases, since it is driven from the kinetic or kinetic theory of gases. We then use this kinematic viscosity, this nu that we end up in here, to relate viscous stress to the strain. And using the physical viscosity to relate a stress to a strain does have a logic behind it. I will try to explain it. The question is, when we use the eddy viscosity to relate turbulent stress to a strain, can we keep the same logic or not? In a simple laminar shear flow, there is not even any turbulence. This could be a laminar boundary layer, laminar vortex shedding, laminar wake behind the cylinder, or anything else. In this type of flow, the ratio of molecular time scale, I'm right now talking about this molecular time scale, which can be calculated by lambda over c bar. The unit is in seconds, molecular time scale, to the shear time scale, which is related to the strain rate. So it's du over dx. So inverse of it is dx du, which is in seconds again. This ratio of molecular time scale lambda over c bar to the shear time scale is very, very, very small. Okay, so you can write it. It's very small. So your s will be equal to du over dx, du1 over dx2 actually, and the order of magnitude of this du1 over dx2 will be u over l. Actually, the order of magnitude of this thing is in the order of 10 to the minus 10, which indicates that things happening in the molecular scale are very fast. The time scale is very small compared to the shear time scale. In other words, it means that if in a laminar flow you apply some shear, you apply some gradients, so you remember that this is your x1, this is your x2, so I'm talking about du1 over dx2. So how much your u1 velocity is changing in this direction, in x2 direction. Okay, so if it is a laminar, let's say boundary layer, for example, if you apply this du1 over dx2 shear, the molecules of the fluid will adjust themselves very, very quick with that shear. It is almost instantaneous. So you will not even feel any lag. So it happens because of the time scale ratio of the order of 10 to the minus 10. Because of this fact, it does make sense to relate viscous stress to a strain through viscosity, through this viscosity. Viscosity definition actually includes the molecular time scale. It has C bar and lambda itself. So to patch up, the molecules adjust themselves very quickly to shear, so the molecular information to derive viscosity, and we use viscosity to relate a stress to a strain. So the molecular motion rapidly adjusts itself to impose a strain. We can write it like this. But what happens when you have turbulent flow? We know that turbulence is macro scale event. It's not a molecular event. It's not micro scale event. Somebody proposed another viscosity. Somebody proposed nu T viscosity to relate turbulent stress to mean strain. The question is, can the turbulence also adjust itself quickly to this strain if I apply a shear strain, meaning that if I apply a velocity gradient to the existing turbulent flow, can it adjust itself to that strain? We check now the ratio of turbulence time scale, okay, to the shear time scale. So the ratio of turbulence time scale, you know that it is k over epsilon. It should give you something in seconds, turbulent kinetic energy over turbulent kinetic energy dissipation rate. We have seen before that this integral time scale tau is equal to k over epsilon. So the ratio of this Turbulence timescale to the shear timescale will not be small. This means that if there is some straining applied to turbulence, it cannot adjust itself very quickly to this strain. What we have in eddy viscosity model is your stress, turbulence stress is a constant times strain, which suggests that with any small change in strain, the stress should change instantaneously. This is linear variation, and it is actually is instantaneous variation. In reality, it doesn't happen like this. There is always a very significant lag. So, as an example, I put two of these. Uh, the first one is for a round jet experimental data. This ratio is about 3, and for a homogeneous shear flow, it is about 6. So this is not a good news for eddy viscosity turbulence models. Therefore, as a patch up, turbulence does not adjust rapidly to the mean strain, and actually there is no justification for a relationship between turbulent stress and strain. So people have observed that only for few instances where a straining happens relatively slowly, meaning that there are not many sharp velocity gradients in the flow field, the eddy viscosity assumption based models could work. But in other cases where there is rapid straining, which generally occurs in many engineering applications like stagnation point, boundary layer, and etc., those models will perform very poorly. So, in simple shear flows, if the turbulence characteristics and mean gradients change relatively slow, the eddy viscosity hypothesis might be reasonable. Generally, in these cases, your production is somehow equal to your dissipation rate. And after this, we can talk about the final deficiency, or let's say final example of the deficiencies of turbulent viscosity or eddy viscosity hypothesis, and it is the fact of principal axis alignment. So, okay, the eddy viscosity hypothesis implies that your anisotropic part of a stress tensor is Aij, okay, and it is this model actually implies that this Aij is aligned with Sij bar. In other words, their principal axis should be aligned. But this is not necessarily true. The principal axis may be misaligned. And in fact, it's been shown in some turbomachinery flows and some other complex flows that your it's not like this. When I say aligned, I'm referring to the eigenvectors. So this hypothesis, the turbulent or eddy viscosity hypothesis, assumes that Aij and Sij have the same eigenvectors. For example, it's been shown that in the wakes of the rotor of a multi-stage turbomachinery flow, this is not true. They are not aligned. Not only that, but also in some turbulent shear flows, we may have uh, S11, S22, and S33 all equal to 0. And in this case, the eddy viscosity model predicts that if the normal strain is 0, the normal stress should be 0. But that is not always the case. After all these problems, you should ask yourself, why do we use the models at all? These are some major problems we are talking about. These are not specific problems to any of the models like K epsilon or K omega. These are the problems of the starting point, the Buzynsk assumption. The thing is, the Rand's equations are much easier to solve. You can have a very quick solutions, and if you don't have a very complex flow field which does not necessarily ask for advanced turbulence models, still Rand's solutions are preferred. You can guess that when solving Rand's equations, the time step and spatial resolution is very coarse compared to LES grid or DNS grid. You can get very quick solution, and this is attractive, obviously. Apparently, none of those problems exist for DNS or LES. However, some advanced turbulence models uh, care about some of these above mentioned problems, like the history effect and the stress strain alignment problems and others. Generally, the academia in the world left, abandoned the research on RANS, and they moved to other approaches. RANS is the business of the industry, but more academic research, 800, 80% of the research is dedicated towards LES and new subgrid scale models, a priori and a posteriori testing, doing experiments to develop new subgrid scale models, and so on. Some people still develop RANs, but not in the majority. When you have, for example, a DNS simulation of isotropic turbulence, using that data set, you can test many of these things as well. What we are going to do in the next few minutes, uh, as students who are taking the turbulence class, you have to be aware of what you're dealing with when at work you are using softwares. It's not like 20 or 30 years ago. You are not writing any codes anymore. You have CFD codes, commercial codes, you're using them like black boxes, and they give you very pretty pictures. Sometimes you see very irrelevant problems as well, like a CFD on a cow or even on a dinosaur. But you have to be aware of what you're dealing with. You have to be aware of the fact that what you're getting may completely be wrong. The mean flow field, pressure field, velocity field, they may not be completely wrong, but some little detail may be completely wrong, and those details may cause a disaster in your engineering application. So you have to be aware of these things. Traditionally, after talking about the details of eddy viscosity models and Buzynsk assumption and its problems, we now go on the models. How the Buzynsk assumption is in reality implemented in terms of the models that we use. And we will start with the simplest one, which is the algebraic model, and we will go towards more complicated ones in the literature. Okay, uh, what actually, what are these algebraic models? They have only one purpose, and that is to find the value of eddy viscosity or turbulent viscosity. Eddy viscosity, we said it is a constant, but obviously it can change from one location to the another location, so it is spatially changing, and it can be time dependent as well. So these models are trying to find the correct distribution in space and time of eddy viscosity. So as you know, Reynolds introduced this decomposition and averaging process, and very quickly after that Buzines came up with the assumption of relating turbulent stress to mean strain, and again very quickly after that Prandtl came up with the first turbulence model in the early 1900s. So we call it today as a mixing length model, the Prandtl mixing length model. What is it? Actually, it is the most basic of all turbulence models. It is the simplest and the quickest way to get value for turbulent stress. If your flow is not very complicated, if it is a simple two-dimensional boundary layer on a flat plate, it could still give good results. What this model actually do is, in short, it is trying to find a value for eddy viscosity, and as we said, we do not know exactly what it is, but it has a unit of viscosity, meter square per second. So in general, it could be represented, this meter square per second, generally you can represent it by a meter multiplied by meter per square. So it is a multiplication of a velocity and a length scale. So I call this length scale L star, I call this velocity as U star. So, so that when you multiply L star by U star, you will get the consistent unit. At least its unit is consistent. It was proposed for two-dimensional boundary layer flows, that nu t is equal to Lm squared times the magnitude of du bar dy. The reason is that in here we need to use a length scale L star and a velocity scale U star. So for length scale L star we use what we call a mixing length Lm, or we call it sometimes a Prandtl mixing length. And for the velocity scale U star, we use the same mixing length times a strain magnitude, where in two-dimensional boundary flows, it will be simply du over dy. So when we combine these two, it becomes like Lm squared times du over dy. You see that every time you get rid of one question, it generates another new question. So now we have a model for nu t, and it says that is a length scale and a velocity scale. Now the question is, what is this velocity? What is this length scale? Lm. Is it universal? Does it depend on geometry? Does it change with time? How it is distributed in a turbulent pipe flow? Is this distribution different in turbulent boundary layers? There are several questions that need to be answered. So people have worked on uh, this, and there are many different versions. Generally, Lm is a function of space. And it is, as it is written in here, is an input to your numerical solution. That is the worst part of it. This is not solved. This is not a part of the solution. It has to be an input to your solution. So LMX has to be specified before you start solving or integrating the equations. And even worse, this Lm is geometry dependent. So you might have a distribution of Lm for a flat plate boundary layer completely different than that for a cylinder wake or for an aircraft wake. Over the years, in the first half of 90s century, people proposed modified versions of LM. For example, you have Smagorinsky model back in 1963. You have Baldwin and Lomax, uh, let's say, model or version, which is Lm squared times omega, where this omega is the mean rate of rotation. So instead of a strain rate, it relates nu to the rate of rotation or rotation rate tensor. These were proposed to be used in all kinds of flows. People have studied this extensively, and we have the Jebejee-Smith algebraic model meaning that you can see in here, you all see that these are it's a simple one equation. You don't need to solve any additional partial differential equation. You just solve one or maximum two algebraic equations. So it's very simplistic and very fast. People have studied extensively in aeronautical boundary layer flows and developed new models like, as I said, Jebejee-Smith model. The, so the Jebejee-Smith is from 1967, and also we have Baldwin-Lomax model, and these models provide mixing length specifications that give quite good results for attached boundary layers. If you're dealing with a relatively simple attached boundary layer case, you can still use the mixing length distribution provided by Baldwin Lomax or Jebejee Smith models, and you can use these equations to estimate other flow properties that you are interested. But of course, you can see these are very, very limited. If you go to other flow cases where there is some partial separation or a complete massive separation like these models do not work. So it was a first attempt to come up with an additional equation to calculate the turbulence stress started by Prandtl and then modified by Smagorinsky and Baldwin and Lomax and Jebejee and Smith. Then people realized that these are good, but very simplistic. They need more advanced models because the engineering flows are actually more complex. Then they said, okay, the next step would be to have powerful enough computers, so let's derive additional PDE or partial differential equations so that we can directly solve for turbulent kinetic energy. Because we need eddy viscosity and it is related to the turbulent kinetic energy, right? And also the dissipation rate. Instead of the simplistic assumptions, we do not know, first of all, what is mixing length. It is completely artificial parameter. Instead of doing that thing, let's derive a transport equation for quantities that are relevant. For example, uh, for turbulent kinetic energy or dissipation rate, K and epsilon, and then solve those equations as a part of the solution. That brought in the first attempts towards non-algebraic models in early 1970s, and that brings in additional partial differential equations, and today we call them as either one equation or two equation models. Two equation models like k epsilon, k omega, and etc. We have advanced versions that still persist until today. But at the end, what you do is you try to obtain a solution field for turbulent kinetic energy and dissipation rate, epsilon, and then use those values to calculate the eddy viscosity and then the turbulence stress.